goal of this lab is to determine the unknown concentrations, the pH, and the pOH of 3 different acids by titration.
Titration is the controlled addition and measurement of a known solution to an unknown solution until the reaction reaches its equivalent point, which is when the two solutions are in chemically equivalent amounts. The equivalent point can be determined by an indicator called phenolphthalein. The indicator will change colors, and this point in the titration is known as the endpoint of the indicator. In this lab, goggles were worn to protect the eyes from any contact with chemicals such as acid. Gloves were also worn to protect the hands from contact with the chemicals. Aprons were worn to protect clothing from the chemicals as well. Long hair was pulled back, and closed-toe shoes were also worn. Two burettes were set up, one for the acid and the other for the base. The acid burette was cleaned by rinsing the burette 3 times with the acid being used. The same thing was also done to the base burette. The acid burette was then filled to a point above the 0 milliliter calibration mark with the acid of unknown concentration. Some acid was then released to get rid of any air bubbles, and it also lowered the volume to the calibrated portion of the burette. The volume of the acid in the burette was recorded as the initial volume. An Erlenmeyer flask was then placed under the acid burette, and 12 milliliter of acid was released into the flask. The initial volume reading was subtracted from the final reading, and it determined the exact volume of acid released into the flask. 3 drops of phenolphthalein was then added to the flask.
The other burette was then filled with the standard base solution to a point above the calibration mark. Some of the base was then released from the burette to remove any air bubbles and to lower the volume to the calibrated portion of the burette. The volume of the base was then recorded to the nearest 100th milliliter. An Erlenmeyer flask was then placed under the base burette. Slowly some base was released from the burette into the Erlenmeyer flask while constantly swirling. The pink color of the indicator faded with swirling. More base was added until eventually the equivalence point was reached and a light pink color remained after swirling for 30 seconds. Then the initial volume was subtracted from the final volume, giving the exact volume of base released into the flask, and this value was recorded to the nearest 100th milliliter.
Yes! Done. Now Lillian's going to take a swig of it.
This is the data in math for acid A. The mathematical calculations were done the same way for the acids A, B, and C. On the top, the balanced chemical equation for the reaction between the acid HCl and the base NaOH can be seen. HCl plus NaOH yields NaCl plus H2O. Below that, the data recorded during experimentation can be seen in the boxes labeled initial volume reading, final volume reading, and volume used. Using the data collected in the volume used box, the average volume used was found for both the acid and the base. And this was done by summing the volume used in trials 1, 2, and 3 and dividing by 3 to find the average. The average volume used for acid A was 11.93 milliliters, and the average volume used for the base was 8.20 milliliters. From there, the average number of moles used for the acid and the base were able to be calculated. Since the molarity of the base was already known, this was calculated first. Using the equation for molarity equals number of moles divided by liters of solution, the value 0.00161 moles of NaOH was found by solving the equation 0.196 molarity equals X moles over 0.00820 liters. Because the mole ratio between HCl and NaOH was 1:1, the average number of moles used for HCl was the exact same as the average number of moles used for NaOH. From here, the average molarity was able to be calculated. Again, this value is already known for NaOH 0.196 molar solution. Then using the equation molarity equals number of moles over liter solution, the average molarity for HCl was able to be calculated by solving molarity equals 0.00161 moles divided by 0.01193 liters, which gave 0.135 molar solution HCl. From here, the average concentration of H3O plus ions was able to be found. This number for HCl was the exact same as molarity, 1.35 times 10 to the negative 1. Using this number, the average pH was able to be found by solving for the equation negative log of the concentration of H3O plus ions equals pH, or negative log of 1.35 times 10 to the negative 1, which equals 0.870. This was the pH of HCl. From here, the average concentration of OH minus ions was able to be found by solving for the equation H3O plus concentration times OH minus concentration equals 10 to the negative 14th, or 10 to the negative 14th divided by 1.35 times 10 to the negative 1, which means the concentration of OH minus ions was 7.41 times 10 to the negative 14th. Using that number, the average pOH was able to be calculated by doing the equation negative log of the OH minus concentration equals pOH, or negative log of 7.41 times 10 to the negative 14th, which gave a pOH of 13.1. A similar process was repeated for solving for the pH and pOH of the base, except the average OH minus concentration for the base equaled the molarity of the base, 1.96 times 10 to the negative 1. Using the average OH concentration found, the pOH was able to be calculated first for the base, using the same equation as used for the pOH of the hydrochloric acid. Negative log of the concentration of OH ions equals the pOH, or negative log of 1.96 times 10 to the negative 1 equals 0.707. Using this, the average concentration of H3O plus ions was able to be found for the NaOH solution, using the equation H3O plus concentration times OH minus concentration equals 10 to the negative 14th, or 10 to the negative 14th divided by 1.96 times 10 to the negative 1, which gave it H3O plus concentration of 5.10 times 10 to the negative 14th. Using this, the pH of the NaOH was able to be found using the equation negative log of H3O plus concentration equals pH, or negative log of 5.10 times 10 to the negative 14th, which gave a pH of 13.3. Our data ended up being very close to the averages of the class. The possible errors in this experiment were possible imprecise readings of measurements and possibly letting too much base in to the solution before it turned pink.